Hello everyone, it's Dr. Wolf here, and in this video I'm going to be going over anaerobic cellular respiration, specifically fermentation. So this is going to happen when there is no oxygen. So though that would be aerobic conditions, this is not aerobic conditions, which means that this mitochondria not going to be involved in the process. All right. If we're talking about certain types of prokaryotes like bacteria, they don't even have mitochondria, right? So this is all going to be taking place in the cytoplasm. All right, and where we're going to actually start this story is with glycolysis, right? We have a glucose molecule, and we're going to break it up into two pyruvate molecules. All right. Now, in doing that process, all right, there's some stuff I'm not showing here. We had to have a net input of not a net input, but 2 ATP go in, right? Investment, and then we get 4 ATP. So as a result, we're getting some energy, right? We're getting 2 ATP molecules out of this process of glycolysis, right? These 2 ATP molecules, all right? In doing so, making our pyruvate molecule, right? Okay, what we also got out of this by splitting our glucose molecule up into pyruvate is some NADH, all right? Which could go to the electron transport chain in aerobic conditions, all right? So here's the thing though, NADH, it really can't go to an electron transport chain because that's in the mitochondria, and we're not doing the mitochondria in this video, or an organism literally may not even have it, right? So here's the problem, all right? In order for glycolysis to continue, all right, we need, right, NADH to pick up those electrons, but the problem is these electrons are already here, so if I get a new glucose molecule and I want to hop electrons over here, it's already taken. In other words, I need to get rid of these electrons because I don't have an electron transport chain anymore, all right? So the first type of fermentation, all right, that we're gonna be looking at here for this is going to be lactic acid fermentation. So lactic acid fermentation, all right? What's gonna happen is, here's our pyruvate, right? Our pyruvate is gonna get an electron, all right? And that's going to cause, all right, that oxygen to become a little bit of negative, that a hydrogen in just the fluid is going to attach to it. And instead of having pyruvate now, we have lactic acid, all right? Now, this happens twice, so 2 electrons jump off my ADH molecule. In other words, my ADH molecule's been oxidized and my lactic acid's been reduced, right? So now I just have this byproduct. Lactic acid is just going to kind of diffuse out of the cell, all right? But what I have now is some new NADH, right? So if I get a new glucose molecule that comes in and I want to go through this process of glycolysis, if I want to generate more ATP, right, I can now break up that molecule. I could get this like the electrons on NADH, right? Again, that process would happen again. These electrons would jump from back to the pyruvate to form lactic acid. That would go away. It essentially allows this glycolysis to continue. So what do you get out? How many ATP do you get out of lactic acid fermentation? Well, you don't really get anything. It's a recycling process, right? It allows you to continue glycolysis where you're always going to get a 2 net ATP out of this process. Now, there's some practical applications for this in terms of food, right? We could use this process to make kimchi, sauerkraut, kombucha, yogurt, cheese. These are all examples of how lactic acid fermentation can be used to make delicious, delicious foods, all right? Now, let's say I'm an organism and I'm not going to do lactic acid fermentation. Oh, real quick, let's talk about the amount of ATP generated. We kind of already talked about it before. We're really getting 2 ATP out of glycolysis, and then fermentation just recycles, allows glycolysis to happen again. But compared to aerobic cellular respiration, where we're getting close to 30, way less. So this is way less energy, and we're getting way less energy out of this process compared to aerobic cellular respiration. So let's jump to the next form of fermentation called alcoholic fermentation, all right? And in alcoholic fermentation, same idea, right? Glycolysis has happened. We've got our our ATP. We've got our NADH with our electrons on it. All right, we've got our pyruvate as the product of that process. And now, in order for this process to continue again, right, we need to get rid of these electrons. All right, so it's really similar to the last process, but instead, what's going to happen is this pyruvate, a carbon's going to break off. All right, so this carbon is gonna carboxylate essentially and create CO2. What's gonna be left then for 2 carbons is ethanol, all right? As a result, or technically it's actually this other intermediate, all right? And that other intermediate is gonna pick up in electrons, and then that's gonna now form ethanol, all right? That's gonna happen twice, all right? So what I have now is some free NADH, right? So when my glucose molecule comes over again to do glycolysis, it could do that because now this NADP plus could pick up some new electrons. So we're getting ethanol out of this process and carbon dioxide, okay? Now, food applications would be kombucha again, bread, beer, wine, all of these use alcoholic fermentation, all right? Notice it's the exact same thing, amount of ATP generated in this case. And by the way, if we go to glycolysis, just a little bit going back to aerobic cell respiration, this is an example of substrate level phosphorylation. Makes sense that it wouldn't be oxidative because there's no oxygen present in this scenario, right? So this is just gonna be mediated by enzymes getting this ATP, all right? Thanks for watching, everyone.